Hi everyone. For this exercise, I have prepared a tutorial that focuses on how we can extract a topology information from a NURB surface and model panels that can have some sort of filtering mechanism and parametric application for internal voids as well. So for this exercise, the script is going to be executed in three parts. First, we're going to look at how we can work with a surface and generate kind of an offset surface using graphs. And then in the second part, we're going to look at modeling triangular panels. You can also use some other software like Lunchbox tools to get triangular panels on a NURB surface. But in this tutorial, I'll show you how you can do them from scratch. And in the last part, we're going to filter the panels basically into two, and we're going to define which ones are larger than the average value so that we can create some voids in them. And the second group, we're just going to treat them as closed panels. So for this exercise, I'm just going to output the end result. So as you're seeing, the end result basically is made out of triangles that are guided by the distortions in the topology. So that topology is driven by a NURB surface. So for this exercise, we're going to input a surface, but the advantage of it would be that if we change any type of geometry information on the surface, our script will respond and execute accordingly. So in this case, I can make some topological changes, and here you're seeing that the triangle sizes are changing and the panel configurations are changing simultaneously as well. So this type of modification will be really handy once we use surface inputs to drive our script. So I'm going to delete this for now, and what I'm going to do is start from scratch so that we can see how this is done. First thing is, let's model a simple surface in Rhino. So to do that, I'm going to use a curve like this, but you can also draw it manually. You can also start by, let's say, defining it kind of an L shape. I'm thinking of this kind of a surface that can act as a wall or a ceiling, or can connect both of them. You can also do it the other way, so it can start from the ground and go up as well. And I'm going to use the rebuild command and increase the point count to 4 and degree to 3. And then I'm going to move some of these points around so that we can get a little bit of the continuity of an edge condition, right? So this should look like a rounded corner. After I draw the profile in the side view, then I will move on to the perspective view, and I'm going to start with a simple extrusion. So keep in mind that after we build our script, we can also change the information on the surface and give it any type of shape we want. So at this phase, we can just start with a simple surface, and I'm going to explode this so that this will be converted into a NURB surface. So sometimes extrusions do not read as a good input for Grasshopper. And the next step is to load this into Grasshopper. So I'm going to create a surface tool container. Basically, you can find it under Parametric surface. And then I'm going to right click, choose Set One Surface, and choose the Rhino Geometry. So now this plugin will be light gray, so it will be linked to this Rhino Geometry. And for the sake of the exercise, I'm now going to continue in Grasshopper, so I'm going to hide the Rhino Geometry. And every time I select this, you can see that the Rhino Geometry is being highlighted as well. So we can, after executing our script, we will have the option to change our input and see how it responds with the script as well. So the first step is to divide the surface into points that we can use to create an offset. And for that, we can do divide surface command that extracts UV points from a surface. And you can find this under Surface Tools Utilities. And I'm going to connect my surface. Now, since we're going to make triangles, what I want to do is, as you can see, the horizontal dimension and the vertical dimension are different because this curve is a lot longer than this width of this panel. So what I want to do is define the U and V parameters in such a way that these points will be somewhat equally distributed in both directions, right? So I want to get kind of a gridded layout on the surface. So I supplied 34 U values, and we can make another number slider and change this proportionally so that we can have kind of a resolution that fits to our needs. So I'm going to start with 30 in the U direction and 8 in the V direction. The next step is to move these points uniformly so that we can see how the normals work. So after I do the subdivision, I get 3 parameters, basically the location of the points, the normal directions, and the U and V parameters. Now, in order to see the normal directions, we can look at vector display, and vector display is located under display options vector, and you can connect the points for anchoring location and the normals for the vector direction. So you can see that these are the normal directions that are perpendicular to the surface at these points, right? So and I want to use this vector information to translate these points away from the surface. So one way of doing that is to use vector amplitude, where we can override any type of vector with a number so that we can increase or decrease the scale of the vector. Don't forget the normals are uniform normals, so the length of these is 1. And if I change it to 5, you can see that we can have a lot more movement, right? So this is how we can offset these points off of the surface. And I'm simply going to move them using these vectors so that you can see now I've created an offset point distribution. And when you look at the data, the important thing is after you use the subdivide surface, if you go over to the point, you can see that the data is actually clustered, so it's in lists. So depending on the amount of U values we placed in, we get 31 lists, horizontal lists, and each of them contain 9 points. So the list goes in the horizontal direction in my case. And what I want to do is actually use Grasshopper in both directions to give a kind of undulating effect for this surface. So to do that, I'm going to create 2 Grasshopper conditions here. So let's choose Grasshopper. And then I'm going to supply a range. And you can find range under set sequence, and the Grasshopper is located under parameters input. Now for Grasshopper, we can right click here and choose any type of graphs. I'm going to go with sine summation for this exercise. And I'm going to simply use these values, because if we supply 30, we actually get 31 lists. So the same thing works with the range. So when I supply 30, it divides the domain of 0 and 1 into 31 equal segments. And I'm going to use this as my input for the first graph. And I want to make a second graph by copying and pasting this one and supply number 8 for the second list. So the idea is that we want to use this profile condition or this graph to control the vertical displacement of the vectors. And I want to multiply it with this graph, which will constrain the horizontal transformation. And you can do it simply by multiplying the output. So you can treat these as percentages. It will give you values between 0 and 1. And I'm going to multiply them. But when I multiply them directly, you see that we actually get 31 values. And here, if you look at the data, we have 279 values. So I need a data set that somehow mimics this lists within lists, right? So I need 31 lists containing 9 values each. And to achieve that, we can simply graft one of these streams, and grafting it will actually use this amount to multiply it uniformly with every amount at the bottom list, right? So if 9 values are coming from this side and 31 values are coming from this side, if this data set is grafted, then the output will be 31 times 9, creating 31 unique lists. So all of these values will be individually multiplied with all these values. And now we have 279 values that match the amount of points we have. And what I want to do is also multiply the end result with this overall coefficient that we have so that we can amplify the matrix that we are creating. So you can treat this as kind of a two-dimensional matrix, and this is an overall amplitude. So the mixture here will create some sort of percentage for every point as a two-dimensional data, and then we can change the amplitude of it. And I'm going to use this final multiplication to drive the vector displacement. I'm going to hide the vectors for now. And here you can see that we are actually controlling kind of a different type of transformation, right? So I'm getting some sort of sections that mimic these graphs. And if I move these graphs around, you can see that the data is also changing. So this controls kind of the section distribution, whereas this will control the kind of planar distribution, so horizontal distribution. And you can also use different sets of graphs. So if I make it as a Bezier, you can see that here the data is closer to the surface because the initial values I'm feeding are small, whereas the later values are larger. So this will create the type of offset I want to create from the surface. So this actually defines the end of the first point we want to arrive, and I want to finalize this by turning each horizontal row as a polyline. So polyline, and you can find polyline under curve spline, and each row will be turned into a polyline with this command. And I want to simply flatten this list out so that we can work with it. So what I want to do next is connect each of these rows using triangles. So this line will be connected to this line by building triangles. And to do that, we first start with the initial list. So we have 31 curves. And since I'm going to connect each curve to the next one, what I want to do is create two sets of lists using shift list command so that we can actually transpose the list to connect or relate each line with the next line in the list. So to do that, I'm going to type in shift list. And one thing that is important, we don't want any wrapping for this for the shifting, because wrapping would actually shift the data and it will put it to the end of the new list, and we don't want that. So I want to shift the list of the polylines, and for shifting we need some index. So we want the index to go from -1 to 1, and you can define a number slider by using this shortcut. You can simply double click on your canvas and type in -1 ... And the first list, I want to basically shift the first item in that list, which is the bottom line here. And we want to mix it up with a second list that actually shifts the data from the end of the list. So you can see that this shifted data doesn't contain this line here. So what this means is that if I now connect this list with this list, you will get a continuous surface. So each line will be lofted to the next line, right? So this one starts from the bottom, but this one starts from one level up. So if I'm looking at it here, it starts from here. So to connect these two, I'm going to explode each curve, and I'm going to actually turn off for now the way we evaluated the surface. I'm going to maybe leave the surface on so that we can see what's happening. And I will start with this group and explode the curves so that we will get points and line segments. So because these polylines are drawn by 9 points, when we explode them, we also get 8 points back, and we get 9 points back in the vertices, and under segments we get 8 segments, right? So there are 8 line segments when we explode them, and there are a total of 9 points. And this means that we can extrude each line segment here. We can extrude each line segment to one of these points on top. So if I extrude this line to this point, then because I have 8 line segments, I need 8 points on the top row. So if I do the same operation to this second list that is shifted, that starts here, I want to go through the vertices here. And you can see that there are 9 vertices, but here there are 8 line segments. So I need to shift the data in the vertices as well. And you can simply make a copy of this shift list command and connect the vertices, and you can see that I shifted the last vertex of each list under the vertices. So this list will contain 8, and here I have 8 line segments as well. So all I have to do is extrude to point. So extrude line to point is located under surface modeling options, under freeform extrude point. And the line segments here will define my curve profile or surface, and the points will be defined by this shift. And once you connect them, you will get your first row of triangles. Now for the second row, we need to look at the line segments here and connect them to the vertices at the bottom. So this will actually require some sort of shifting around, but basically we don't need to do any shifts for these line segments, but we have to do some for the vertices here. And these vertices will have to be shifted in the positive direction so that these line segments can connect to these vertices here, right? So when I extrude this line segment, it connects here. And I'm going to make a copy of the extrusion, and the boundary condition will come from the line segments on top, and the points will come from the shifted list at the bottom. So that will give you the triangulated surface that is offsetted from our input. And here what I want to do is also create a surface container, push these into that surface container. You can hold shift to add multiple branches to the same container. Right click here and flatten that list as well. So now we have 480 untrimmed surfaces that we're going to work with. And at this point, because we're building our script continuously, if you change any of this input, you can see that the surface will react and the data set will change and the triangulation will still work because we are directly building on top of the topological information of the NURB surface. So since the data is continuous, there wouldn't be any type of disruption in the way we built our code. So you can also play around with some of the variation, increase the offset values, change the graphs. You can even change the number of points and it will respond accordingly. So I have, for instance, changed it to 25 in the vertical direction, and we can also increase horizontally or decrease it. So I'm going to move to the end where we have the surfaces. And here what I want to do is some sort of filtering. So I want to actually go through these surfaces, and first I want to extract their wireframe. You can type up boundary representation wireframe. This is located under surface brep wireframe. We get the wireframe or the edge curves of each triangle, and they will be in groups of 3. You can see that each triangle contains 3 curve segments, and I'm going to join those curves. And this is still, if you look at the data, it's grafted. So it's because after the first wiring, we get lists containing triplets. And here I still have the data as a grafted data. And we can right click here and flatten that data as well so that we work with individual polylines. And then I'm going to look at their area value. So type up area and connect the area value. So the advantage of using area is it gives you a center for each triangle and the area value of the triangle. And I want to simply calculate the average value for the triangles so that we can find which ones are below average and which ones are above average. So to find the ones that are above average, you can simply type up larger than. This is kind of a mathematical operator. It's located under math tab operators. And I want to compare the area values to the average values. So the area value goes to A and average value goes to B. And this will compare 2 values and will give you a Boolean output a Boolean output is true or false, so it's binary. If the value is larger than the average value, it will be true. If it's smaller, it will be false. So we can use this to drive a call pattern. A call pattern is located under set sequence, and it basically can go through a list, which could be our boundaries. It can go through a list, and if we supply the pattern to it, it can actually use the filtering mechanism to filter the list that we have. So here you're seeing, because we don't have as much transformation, the larger tiles are located at the bottom and on top, and this middle is actually below average tiles. So the largest area tiles are located at the bottom and on the top. And I can find the remaining values by doing a similar operation, like smaller than. I'm going to compare now the areas if they're smaller than some value. And we can simply look for the smaller cases this way. And you can see that I can now select the smallest area triangles and the largest area triangles. And this is going to become really interesting once we change the input of the surface. So right now the section, the surface is kind of uniform, it's not changing in section, but once I start distorting the surface, you will see a lot more variation occurring. Now for the largest surfaces, what I want to do is actually create a hole inside of them. And one way of doing that is to work with these polylines. So I'm going to first create another area condition to find their center points. We don't need to also filter the areas. We can simply extract them here. And I'm going to do a scale function. So we want to scale the curves. The center of scaling is going to be the centroid of the area. And for the scaling factor, we can use the areas of each triangle as a driver. So I can type in a multiplication here and give it a small coefficient, let's say 0.05. We can also double click on our number slider and set up a threshold. Let's say this goes from 0 to 0.25. And you want the area values to be below 1 so that these pieces will be scaled down. And when I connect them, you can see that I can use different amounts of percentages. So maximum I get is 0.25. The smallest I can get is around 0.05. So this will be kind of a multiplier for the scaling down. And in the last step, what I want to do is turn these into panels themselves. So these boundaries, these pieces, we can simply turn them as boundary surfaces. But to turn this top row, let me actually hide everything before doing this. So this row, these triangles are already converted to surfaces. But to do that to the top part, we actually need to combine this data. So I need to associate each boundary with its scaled boundary, and we can do it by weaving the data. So here we have 176 curves, and here we have another 176, and these are scaled. And if you right click here and graft both of these streams, these will be put into containers of 2, and here you can type in boundary surfaces, so you will get hollowed out panels. And in the final step, we can join these two now. So we can do boundary representation, brep join, and you can stream both of the data, right click here and flatten, so that the end result will be joined into one model. And I'm going to hide this too. Now what I want to do is show you how you can achieve a lot of variation with this tool. So once we bring up the surface in Rhino by typing up show, I'm going to choose the surface and type in rebuild. And with rebuild, we can change the point count and change the degree of the surface. We want to keep it at 3, and I want to increase the point count. So let's start with 6 and 6. I'm going to hit OK. And when you turn on the points, you can actually start moving these around, and you will get actually distorted data on the surface. So by stretching the information between these 2 points, the length is increasing for these triangles, so you can see they are actually being distorted as well. You can also move the surface front and back, and your input will always follow it. You can also stretch it up and down as well. You can also try to use this tool on different types of surfaces. You can also, if I go to the top view, you can also rotate some parts of the surface as well. So for instance, I can do it like this. So I'm trying to maintain kind of a nice shape for the surface, but basically this whole variation will be driven by the surface topology. I'm going to delete the input curve that I had, because now our surface is run by the parameter. And here I have some sort of an issue which comes in from the scaling down. Because the scaling is too much, the boundary surface is not executed correctly, so you can actually decrease this percentage a bit more so that you can get smaller gaps, but here you wouldn't get any errors because those tiles are really big. So let's bake some variation. So go to join, right click bake, and you can see the variation now. So this would be our surface. So I'm going to turn on the rendered perspective. So you can see that I've created a surface that is continuous, and we can it also can filter between large pieces and small pieces, and for the large ones it creates some sort of hollow condition. And you can model a lot of cool things with this. So you can try ceilings, you can try walls, you can also do in between elements like ceilings becoming walls, or floors becoming walls as well. So this is it, and to recap, I'll just show you again what we did. So in the beginning I started with an input surface, and we used surface division and some UNV parameters to kind of multiply it with two graphs. And the important thing here was the surface division gives you graphed data. So here you need to use the first numeric input, but because we want to create kind of a two-dimensional transformation matrix, I had to graft the output of the graphs as well. And then I multiplied the result with the for the surface normals and moved the points, right? So this gives me the first transposition from the surface. So I can change any of these parameters or the graphs, and we will get another type of variation. And then each row, the data comes in as rows. So I first converted them into polylines. So let's go back here to the second step. So I started with polylines, and the first step was to actually filter them. So I created two shifted lists. So basically we want to get a list without the last element, and we want to get a list without the first element, right? So that's how the data will match each other. And this is the list without the first item, and we explode both of them. And here, basically, for the bottom list, we get the line segments, but we extrude them to the shifted vertices of the top list, right? Because here there are 9 points, but we want to get rid of the last one. And we extrude it. Extrude both of those so that we can get triangles. And these triangles are then basically becoming the overall surfaces that we have. And the last step, I first extracted their wireframes, and then we joined the wireframes and flattened that list, so we are working with curves. Then when I looked at the averaged areas and checked these averaged areas using larger and smaller than, which are operators, and this will output you a Boolean sequence, right? So true or false, and you can use that for filtering for the call pattern. And this goes at the pattern, and we supply the lists, and we can find the larger panels in our configuration. And then for each larger panel, I found the centroids and scaled down the boundary condition on the centers and use the area with some multiplication. You can also give any type of percentage here. It would also do the job. So you cannot you don't have to use the area. If you supply 0.9, they will all be uniformly scaled down. And then in the last step, I associated the bounding polylines with the scaled polylines using Weave, and this gives you groups of 2 that you can define as bounded surfaces with holes in them. And in the final step, I did a Boolean join, so that the result, we can simply bake it and all of these pieces will be connected.